right, welcome to my talk. My name's Patrik, and I'm going to be doing a talk on Desmos. And no, we're not going to be drawing Batman. We're going to be doing more fun things like what I had up on screen beforehand. All right? Okay. So we're going to cover a few things that you can do in Desmos, things that are a little bit more than just y equals mx plus b. So we're going to talk about vectors. You can do vectors in both the 2D and 3D calculator. We're going to talk about random numbers and distributions for you stats nerds. We're going to talk about lists, which are an incredibly useful feature in Desmos. Actions, which give Desmos the ability to be Turing complete, actually. And then the different kinds of plotting you can do. And then at some point, I'm going to mention Desmodder, which is a Chrome extension to enhance Desmos. So throughout this presentation, I'm going to use this syntax where I use E1 is defined by E2. And what I'm trying to say is that if you type E1 into Desmos literally, you're going to get the value of E2. And this will help explain some things later on. For the early things, it'll be like 1 is defined by 1, and that's kind of boring. But you'll see what I mean later on. So let's get started with vectors and points. So you can create 2D points, and you can create 3D points. Naturally, you can create 3 points only in the 3D calculator, so I'm sorry if you want to, I don't know, bend the rules of dimensionality. Vectors form a vector space in Desmos up to, IEEE floating point numbers, which it does use 64-bit floating point numbers because it's JavaScript. So to create numbers, to create points, we saw that, and you can add them, subtract them, you can multiply them by fractions, you can divide them. You can't divide two vectors one by the other because that doesn't really make sense. 3D vectors work exactly the same as you'd expect. They just kind of work, so you can do the same thing as with 2D vectors. You can do summation as well over vectors. So for example, if you actually sat down and wrote whatever this expands to, you'll see it does actually value to 55, 110. So you can do a few extra things with vectors, some built-ins for vectors. You get norms actually. So 3 and 4, if you recognize that as a Pythagorean triple, you get 5. 2, 3, and 6, if you recognize that as a Pythagorean quadruple, you bunch of nerds, you get 7. You can do cross products in 3 dimensions. So if you happen to be a wizard at calculating cross products, that is the cross product of those two vectors. You also get dot products for free. And if you want to get a cross product, you type cross, like C-R-O-S-S, to get the times for cross. If you want to get a dot product, you just press like the star key on your keyboard, and that'll put in a multiplication for you. Integrals work just fine over vectors. So if you take the integral, it just takes the integral of the individual components. But this is really powerful because this actually lets you do, for example, complex integrals, if you define what complex multiplication means. Moving on to the next section, and don't worry, we will see some examples. They'll just come after the list section because I need to lay some groundwork so we have something to work on. So for randomness and distributions, we can create distributions. So a uniform distribution will uniformly distribute samplings between the minimum and the maximum value, each with an equal probability. I mean, I guess that's pretty self-explanatory. Normal distribution you can have with the mean and then the standard deviation. That should also be self-explanatory if you passed high school statistics. I still haven't taken university statistics, so I have no clue what any of this means. However, if you have taken statistics, then you can create a t-distribution, a Poisson distribution, and a binomial distribution. You also have a few built-in functions on distributions. So you can create the probability density function, and that just plots it as a value of x. So in this case, we're assuming D to be a distribution object. You also have cumulative density functions rather than probability density functions, and they work as you'd expect. If you only give it one argument, it's implicitly assumed that you're sampling from negative infinity up to the one argument you provided. And finally, if you actually want to sample your distribution manually for some reason, although you can sample it, and we'll see how that works later, you can just say d dot inverse CDF, and then that gives you the inverse cumulative distribution function. So for random sampling, we can just say random, and that gives us one random number. If you say random of n, where n is an integer, you get n random numbers in a list. If you say random of n comma d, then that picks n random numbers from a distribution. You can't sample just one random number from a distribution. You can sample a list of size 1 from a distribution, and then you just pick the first element. Kind of cumbersome, but then again, how often are you sampling one random number from a distribution? If you pass in a list, where L is a list, and I know we haven't seen lists, but we're going to get to them. If you say random of a list and then n, you get n random numbers from a list. And in your graph on the top left, whenever you use randomness in your graph, you're going to see this button pop up on the top left, and that re-rolls the seed so you can re-randomize your graph. So moving on to lists, and bear with me, we are going to see some examples. You can create lists just by saying left bracket, stuff, right bracket, and they work as you'd expect. I mean, we're all in the computer science club, so I mean, we've seen arrays before. You can create ranges, and ranges are inclusive on both sides, so 1 up to 5 includes both 1 and 5. They also will try to determine if you're doing a linear progression. So for example, if you did 1, 1.2, 5, it would do 1, 1.2, 1.4, 1.6, all the way up to 1.5. It'll try to determine where to end and the linear progression that you're looking for. You can also do random sampling, which we already saw. And finally, you've got Python-style list comprehensions built into Desmos. So if you set f of x for x equals L, then that expands to f of L of 1, and then f of L of 2, and then f of L of 3, and all the way up to f of L of count. And yes, actually, Desmos lists are one index, unfortunately. So you're going to have to do plus minus if you're used to 0 indexing, which hopefully you all are. Additionally, list comprehensions are Cartesian products. So down there I've got f of x comma y for x equals L1 and then y equals L2. Well, that'll expand to all possible iterations of L2 and then all possible iterations of L1 for every one. So in this case, we go L1 at 1, L2 at 1, all the way up to L1 at n, L2 at 1, and then we do L1 at 1 and then L2 at 2. An important thing to notice is that lists of lists are not supported in Desmos. So work around them somehow. I don't know, figure it out. You can have restrictions. So let's say L is our list. And you want to pick all the numbers that are less than 3 because, I don't know, we hate the number 3. We've got L and then a restriction. L is less than 3. And then that'll pick out whatever it is you want. If you wanted, for example, if you have, for example, a list of points, and you want all the points which have magnitude less than 1, you can also do that. Any function of L is allowed in there. If you just say a function applied to a list, it will implicitly expand to the function applied to every element in the list. This is pretty useful because now you don't have to do a for expression for each single one. You can also do arithmetic. So kind of like vectors, they form a vector space in that if you do L1 plus alpha L2, you get what you'd expect. And it will, the size of the resulting list will take the minimum size of the first two lists, or the input two lists. You can also do practically arbitrary expressions. So if I've got a list of points and I say L.x, then I get only the x components. An important restriction to notice about Desmos is that lists have a maximum length of 10,000. So that expression will error out. You can work around this using a JavaScript hack if you wanted to for some reason. Yeah. There are a few built-in functions on lists, and we're going to speed run through these. So you can say, for syntax, you can say L.built-in, or you can say built-in of L. Either one works. So if you do L.count, you get the number of elements in it. If you do L.max, min, mean, or total, you get what you'd expect. Stats of L and histogram of L are two stats functions, but you have to call them using the function notation. You can't say dot built-in notation. That's because stats.L will produce statistics on the minimum, the maximum, the mean, and the median. And histogram will actually plot a histogram for you. You can also sort lists, and you can pick out unique members. So, I mean, this list, oh, it wasn't pre-sorted. So it sorts the list as you'd expect, and then unique deduplicates the list. Sorting can also use a separate list for keys. So for example, suppose that I had a list of points, and I wanted to sort them by their magnitude, for example. Well, the list of points and the list of their magnitudes are two separate lists, but I can sort one by the other. And finally, you can join two lists. So if I've got a list of 1, 2, 3, and then a list of 4, 5, 6, and I join that onto the original list, you'll see 2, 1, 3, 4, 4, 2, 1, 3, 4, 4, 1, 2, 3, 1, 2, 3, 4, 5, 6, 4, 5, 6, as you'd expect. And an important thing to notice is that lists can only contain one data type at a time. So for example, this is nonsense. You can't write that down. Beginning with the fact that we've got a point and a number in it, nah. And all that other stuff, oh yeah, you have seen uniform distributions. So let's look at an example. Oh god. Doing examples on this is going to be a bit hard. But, oh god, I really can't see. So we've got folders here, and by the way you create a folder is by just typing out folder. And so if we open this folder, oh god, I really can't see. So if we open the folder, we've got a few things defined in here, and I would explain what they are if I could see them. However, here we are creating a grid of points. Yes, we're creating a grid of points. And so we create the base points. I'm going to disable the actual grid. We create the base points. Hello. Come on. If I could aim my mouse, then that would be better. Yeah, we create the actual grid using a Cartesian product. So this is the for syntax we were seeing earlier. And then we do some shenanigans to get the lines to render. And voila. We can do some more fun stuff if we open the second folder. And we see, so it's the same grid. However, in there I've also chucked the math to define complex exponentiation. So I'm going to take every point on that grid, keeping the grid lines preserved, and raise the number to the point to the power of, what is that value? K. So if I take this, and you've ever been curious what raising complex numbers to a power looks like, here's what it looks like. And you can go the other direction too, because the math just happens to work out really nicely. So yeah, going back. Oh, it's just the wrong window. Why? Why did you do this to me? Leave. Leave. Where's my presentation then? Okay, 1 second. Come on. There we are. All right. We were first example of after lists. It would really help if I could see what's going on. My glasses work, but so here's a more complex example, and this is a 3D calculator. And if you've taken, for example, vector calculus, you'll know that vector fields are a very important thing to look at. And here, all that I've done is I've created a grid, but a 3D grid of points, a 3D grid of 3D points. And all that I've done is I've defined this function, 1, 2, 3 cross product. The vector cross product 1, 2, 3 plus this offset vector, and this creates my vector field. And all that I'm doing is I'm plotting these vectors using the built-in vector function to draw the little arrow, because otherwise, I don't know, you could go insane for a few days trying to figure out how to draw arrows. And we can take a look at what this vector field looks like. It'll start spinning on its own. And this is pretty useful for creating visualizations, for example, in a math class. You've got no clue what the fuck the prof's talking about. And you can use this to actually see what the prof's talking about. Oh my god, that actually makes sense now. takes like 7 swipes on my fucking trackpad. Hold on. What? What's that? No, where? Okay. So, the next step that we're going to look at is actions. So, actions are the way that we get Turing completeness, in a sense, from Desmos. Actions are ways we just do things. So, as an example, if we want the variable v to become the value x, we just say v arrow x. And you type this out by saying dash and then greater than sign. It'll just autocomplete for you. We can pair 2 actions together by just saying one action, comma, the next action. And we can also put restrictions on actions. So if you wanted to, for example, have a ticker that goes up by 1 but then loops around at 10, we'll just say, provided that a is less than 10, we increment it. Otherwise, we roll it back to 0. We can also do things like, for example, crappy Euler integration. So this says this function produces an action. By the way, I haven't mentioned, functions can produce any variable, any data type that you want. You can have a function that produces an action, a number, a point, a list. The world's your oyster. So right here, we've got a function that takes the points and moves them by the velocity, and then updates the velocity as well, given the acceleration. To actually run actions, you have to press this button beside them, but you can also do it 2 other ways. You can enable clicking on objects to assign an action to them, and you can also actually access which action or which object you want to click on using a special index variable. So I'm not going to click on this first example. We're going to take a look straight at this one. So as an example here, I've got a lovely grid of points. And all that I've done is I've made it so that whenever I click on a box, the 4 boxes around it will light up. And if I click on a box beside them, they will toggle. So here you can, I don't know, draw something. I'm a pretty bad artist, so take that as you will. Once again, something I want to reiterate is that all the examples which I've included in this presentation are very well documented, and I strongly suggest you look through them, because I'm not going to go through and explain how all of them work, but they are lots of fun to look at and lots of fun to work with. An important thing to notice is that multiple actions are run at the same time. So, a la Brad Lushman, what we do is we create a new world and we toss the old one out. So it's not like if we're mutating the world. And oh, I can see. I should have thought of this a while ago. Anyway, so here we've got t and a, and all of these do is they increment t, and they set a to t. So if I do this one, you'll see a gets the old value of t. But if I do this one that has them in opposite order, you'll see it does the exact same thing, because it doesn't mutate anything. How am I doing for time? Okay. All right. The next thing that I'm going to talk about is the ticker. The ticker allows you to automatically run an action at a specified time interval. So here I've got run, well, nothing currently, but we're trying to run that every 0 milliseconds. Desmos will default to trying to run it every 16.6 milliseconds. In other words, 60 FPS. There's a special DT variable for use in the ticker field, which gives you the time in milliseconds. So in seconds divided by 1,000 since the last tick. And as an example, we've got this one, which when I run it, we've got the number of frames, so the number of times we've incremented, and the time that's passed. So the time that's passed gets incremented by this special DT variable, and the number of frames just gets incremented by 1 every single time. So we'll see u of t takes in the time that's passed and divides it by 1,000 because we get milliseconds. So if we actually run this, we'll see we're getting about 60 FPS. So we can use this to our advantage. Let's see an example. This is an n-body simulation on 4 points. And this is running in real time on Desmos. And it's not that bad, actually. It is only 36 expressions. It's not that bad, actually. So we can let this run for a little while, or we can actually move on with the presentation. Feel free to read the presentation later. I will be posting the slides, and you can open this and take a look at it later. Play around with it too. I'm going to close this, because as much as I love Desmos, it will eventually start lagging out my computer. Okay. Oh, there was another example. So, if any of you have taken any kind of a number theory class, then you will have heard about Pythagorean triples. So right here I've got a few thousand, or no, not a few thousand, a few dozen Pythagorean triples. And all that I've done is I've created a grid of points around the origin, and I've said, pick out any which are Pythagorean triples. So what I'm going to do is I'm going to hit this ticker, and what this ticker is going to do is it's going to start looking for more Pythagorean triples. And it's going to start aggregating them into a list. And the reason why I'm doing it this way is because our search area has to fit inside of a list. And the search area of 100 by 100 evaluates to 10,000 elements in a list, but that's really small. If you'll notice, we're approaching 1,000 by 1,000. So the ticker is a very powerful construct, and it gives you complete Turing completeness along with actions. Automatic Turing completeness. Well, modulo, RAM. But anyway. So let's move on to advanced plotting. So there's two kinds of plots. Sorry, there's two flavors of plotting, 3D and 2D. And for 2D plotting, you can graph f of x comma y equals g of x comma y relations. Like for example, this plus 1 is equal to y squared. You can also plot inequalities. You can do polar plots, but polar plots have to be linear in terms of R. This is just a limitation of Desmos, unfortunately. You can also plot a polygon, P, where P is a list of points. And that's how I created the grid on the earlier clicker example, which would draw things. For 3D, you can do basically the same thing. You can also plot inequalities. It will plot them happily for you. Very useful, for example, when you're doing a Calc 3 assignment, and you've got a triple integral to solve, and you're looking for the bounds of integration. You can also plot in spherical coordinates using phi, theta, and rho. And instead of polygons in 3D, we get triangles. So yes, you can build a complete game engine in Desmos from scratch if you'd like. You can also draw parametrics. So for example, here f of t is a function that spits out a point. And if you just say f of t, then Desmos will try to draw for t between 0 and 1. And you'll get a nice, this would be a spiral. If you do the same thing with two variables and it produces a 3D point, you'll get a 3D parametric. Okay. You get a 3D parametric and it'll draw a surface for you instead. I'm not actually going to click on that because it's just like part of a sphere. For colors and styling, you can actually create colors and customize what things look like. So if you say RGB, you get an RGB value. For HSV, you get hue, saturation, and value. If you've done any kind of computer graphics, you'll know what this means. But in essence, you're spinning around a color wheel with the hue, and the saturation is how much it looks like pastel color. And you can also change the opacity of objects. Opacity is between 0 and 1 for fully opaque. You can change line thickness for lines and points, and that is naturally between 0 and infinity. And if you've got a list of objects, you can apply a list of colors and a list of opacities and a list of thicknesses to completely reconfigure every single object in the list. You can also create labels And labels will take the color of the point that they're on. Labels can have size, rotation, and position relative to the object that they're attached to changed. Labels can also count as click targets. Labels can have their content styled using LaTeX if you surround it in backticks. And finally, the interesting one, labels can reference object values using $sign notation. So if A is 12 and B is 5, then if we were to type that down there into a label, we would get this rendering in LaTeX on the graph. So as an example, let's see this in action. This is a function on the complex plane, which I plotted. And what I've done is I've sliced all the possible angles of the complex plane. I've sliced it, I think, 10 times. Yeah, NS is 10. I've sliced it 10 times into 10 slices, and I've assigned a color to each one according to the color wheel. I've evaluated the function at every point, and then I've taken its angle, and then I've matched the angle of the output of the function with whatever color I assigned to the color wheel in that slice, and I plotted it as an inequality. And this is fully interactive. If I zoom out, it works just fine. This isn't an image, it's something I've actually created on Desmos. As another example, let's take a look at a label example. So, if you've ever wanted to time yourself, but don't have a timer ready, Desmos has got your back. So, because labels allow you to completely introduce values from your expressions, you can just have expressions in your labels and you can create a timer. And this is accurate to, I don't know, whatever Desmos here will say. I mean, don't use it if you need like an atomic clock, please. Where's my mouse? I did not change that text. Okay. Well, I'll just stand in front of it. Okay. Thank you for coming to my talk. I hope you enjoy the rest of Alt-Tab, and I hope to be here again sometime in the future. Thank you.
Hello. Hi.
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 Surprisingly, I was not the first person to mention Python tonight. So before we start, has anyone done competitive programming in the past? Yes? Do you know why the competitive programming people say not to use Python? They say Python is interpreted, therefore it must be slow. But I'm here to tell you that Python is actually compiled, so they're wrong. Except Python is still slow, so you shouldn't use it in competitive programming. Before we get into that, who am I? I'm Ivy. I'm in 2A CS. I'm also known as Hexadecimal Dinosaur Online, and I participate in the CTF team SillySec as a forensics and reverse engineering specialist, which is why I dig into all of this random crap. And I do malware analysis in my free time. So this laptop in front of me has way too much malware sitting on its hard drive. So what do I mean by Python is compiled? Normally when we talk about compiled or interpreted languages, we say that compiled is source code that is converted into a binary using a compiler or linker, like C, C++, Rust, Go, or Haskell. And when we say a language is interpreted, we say that the code is parsed and executed line by line by an interpreter, like Bash, PowerShell, JavaScript, or Perl. You might have noticed I've purposefully not included Python in either of these lists, because Python actually sits in a really weird middle ground called bytecode compiled or transpiled languages. And the most obvious example that you probably know of these kinds of languages are Java, where your code gets compiled to a .class file, which is said to be platform agnostic and just runs anywhere that the Java runtime is installed. Python is really similar, compiles the source code to PyC files, but the big difference is that it does it all for you, so you don't actually see any of this step, usually. So when I'm talking about PyC files, they are compiled at runtime. They contain Python code objects, which contain a bytecode representation of your source code, and they're usually stored in the PyCache folder. So if you've ever been working on really big Python projects and see this folder pop out of nowhere, it's the Python compiler doing its work. But these PyC files can actually be executed on their own. So if you feed the PyC file into the Python interpreter with Python and then pass to whatever the file is, it will run just like you normally running any other .py file. So what do I mean by a Python code object? So every time you run a piece of code in Python, so like and declare some definite class or method, it will automatically just compile that the moment you declare it. So you'll see that it has a hidden attribute for that method called code, which is a code object, and this code object contains the bytecode for that method, as well as some other attributes like what variables and constants does it use, what names does it use, how many arguments does this method take. But that's not the only way to compile stuff into PyC files. There's actually a built-in method in Python just called compile, which will take anything you throw at it and compile it to a PyC file, which is cool. And there's also a built-in command python-m compile all, which will automatically compile everything into your PyCache. So what does Python bytecode actually look like? I've rambled on about it for quite a while. So in Python, there's a built-in library called dis, which is the built-in disassembler. Throw any code object that you want at it, and it will just disassemble the bytecode and show you it in a really nice representation like this. The first number from the left is the line number where it's located in the original source code. Second number is the instruction number. Third is the instruction, and then it's followed by any arguments that that instruction has. And Python bytecode runs in the Python virtual machine. And when I say virtual machine, it's not like QEMU or VirtualBox in the sense that it runs an entire operating system. It's a virtual machine in the sense that it has its own special instruction set separate from your CPU architecture. And Python bytecode is also a stack-based instruction set. So what do I mean by stack-based instruction set? So I'm just going to run through this set of instructions, which is actually from this hello function that we seen earlier. So we have the instructions on the left and a stack on the right. So the first instruction is a load global, and it's been told to load the print function. So what it'll do is it will load the print function from the standard library and toss that onto the stack. Next thing we're doing is loading the constant hello as a string. That goes onto the stack. Because in Python everything's an object, so this stack is just storing objects, including the functions. And then it's getting the variable name, which was one of the arguments that we passed to this function, which then goes onto the stack. We finally are going to do something with this stuff on the stack. We have a binary operation instruction, which in this case has been told to do the plus operation. So it will consume the top two objects on the stack and add them together. So we get hello plus name. Adds them together, pushes that result onto the stack. And now we're loading another constant, adding those together, and then we finally get to the call. There is this pre-call function, pre-call instruction in between. Pre-calls don't do anything, you can ignore them. So the call instruction takes one argument, and it's the number of arguments that the function next on the stack needs to run. So in this case it's 1, so I'll just consume this one argument, and then consume this print function and run that. So it will print, and then because print actually returns a none value, that also gets pushed onto the stack. And then, yay, we've finished the execution of this function. There are a few other instructions, just popping this none, and then loading another none because Python did not optimize any of this. Which it then returns because our function that we had from earlier didn't have a return value. There are a few other things that I want to show because they have a little bit of pipe. So if you see, this is the original code that I have for this on the left. It doesn't import, so imports look like this. It takes a name where you want to store whatever you're importing to, and then imports from the library and stores it like any other variable in bytecode. And then every instruction that you are storing gets stored as another code object. So if you have one code object that contains all of its constants, which include functions that are code object constants within code objects. It gets kind of hectic really quickly, which is why I made this really weird tool that is kind of broken to navigate it all, because normally you just have to stare at all of this from the console. Yeah. So why is any of this useful? Honestly, for 99% of Python programmers, it isn't. Python takes care of all of this for you. Yeah, you don't really need to know any of this unless you're like want to become a Python contributor one day, or are weird like me and store too much malware on your computer that you need to rip apart and are scared you're going to infect yourself. I just wanted to make a silly joke about competitive programming, so here I am. But if you are interested in more of this, the Python disassembler libraries documentation the library that I said earlier, has examples on how to disassemble stuff, and then also has a lovely list of every single Python bytecode instruction and what it does. And there's a couple blogs and books about how Python works. And if you actually get into this, the built-in disassembler kind of sucks. I recommend using xdis instead. Yay, that's my talk.
Okay. Hi.
Hi.
I hope you all had a lot of fun the past two talks. I certainly did. And I think my talk is a lot lamer than the other two, but it's okay. If you want to follow along, you can find my slides on that link. I don't really have like a short website link. I should have put a QR code on there, but you know what? Maybe I'll do that after. But yeah, why is my machine learning model so bad? No, this isn't a diss at myself specifically. This is a diss about machine learning models in general. What the fuck? Wait, that's not video. Are we good?
Yeah.
Camera good?
Yep.
Okay. First off, a bit about me. Obviously, I'm SAT. I'm 3B CS. I like programming algorithms. On the lookout for Fall 24 internships if any of your recruiters. I'm single? Okay, that's fine. So
Is this just a very slow transition?
I'm trying to look for a nice word for that. Okay, what is machine learning? So, machine learning is a branch of AI that focuses on imitating the way humans learn and gradually improving accuracy, according to some IBM article. The current state of ML? Well, that one's subjective. Lots of money going into it, though. We will analyze a common problem. Given a set of data, find a function that best fits it. How many of you have studied machine learning or like have heard of this type of problem before? Most of you. Wow, that's a lot of people. Why is this problem important? Also, what is this problem? This is known as a regression problem. It allows you to analyze the relationship between two or more variables of interest. If you get a good model, you can sort of just predict things. Just, after you train your hypothetical example model, or magical model, you can just put any new training testing example in it, and you get an output. It's really cool, and it has a lot of different aspects. So I'm going to show you a demo of what regression can do. So I'm given a set of data points, which is just from some scikit-learn data set. And I'm going to try to find a line that best fits it. What direction of line do you guys think would fit that? Down? Good try. It's the other option. It's up. So yeah, that's an example of what a line would look like. And this is actually a process called linear regression. And don't worry if you don't know what that means. I'm going to explain everything. So what did I just do? So with a linear model, I tried to fit a function, and that process is called linear regression. So using the data points, if I call it x, y, yi from I equals 1 to n, where n is the length of our data set, the objective of linear regression is to find a function f prime such that it gives the value of that expression. What is that expression? It's the difference between the predicted model minus the actual value observed in the data set. And this is like the sum of squares. And so you'll notice that this is like the difference between what the model predicts and what you you intended to have. And so that difference is known as a residual. I'll show you what a residual looks like in case you're confused. But there are other types of regression, or like ways of optimizing. But this is by far the most common, and it's implemented this way in libraries if you don't specify anything. So residuals, you see, if I take this point right here, then this difference, like this is what the model predicts for this input, because it's like a line, right? So if I have this x value, then the y value would be here. That is what we like to call a residual. And you see that right there. I used a different line, but you get the idea. A residual is like the error or distance between the predicted value and the actual value. I can show you this code, or should I show you the code now, or should I show it to you after? Let me just show you now so you get like an idea of how simple it kind of is to do this sort of thing. So this is just a Jupyter notebook, which is just an interface for running code in cells. So I'm importing some basic libraries, and notably sklearn or scikit-learn, where we'll get our data set. So we're going to use the diabetes data set because why not? And we'll see that diabetes X, it has a shape of. So I printed out the shape of diabetes X. So it's 442 times 10. So there's 442 data points of the X values in diabetes, and there's 10 things. There's 10. What's the word I'm looking for? 10 variants as inputs. And then diabetes Y is our output, and so it's just a singular value. Now, the linear regression I showed you had one input and one output. So what I simply did is I just chose the axis 2. or I just chose the third variant because it's 0, 1, 2. And then I can plot the points and then show the linear regression model and then the individual residuals. Don't look at the mean squared error, that's kind of a spoiler. But yeah, so I ran this code, so when you look at my slides later on if you want to, you can run it too. Okay. So if you noticed, our line didn't go through every single point. In an ideal scenario, wouldn't you want the line to go through every single point that you had? Is that always even possible? Not always. There sometimes may always be some error. Just try to think. When would there be such an error? Like when do you think it would be kind of impossible for a function to be able to approximate a set of points? Just toss answers out there, anyone.
2 points have the same x value,
2 points have the same x value and?
different y values.
Yes. Or you could have it as the points, the x values are very close to each other, but the y values differ a lot. But essentially the same idea. It's just there's so much behavior going on in between these points that it's not realistic to be able to expect that our model could approximate this. Totally not with simple, especially not with simple linear regression, which is just a one input, one output, and we're doing a linear regression model, which is just a linear a line that we're looking for. So recall our original goal. Remember that we're trying to find some function f prime that is the exact value of, that is the exact function that minimizes the difference of that minimizes the sum of the squares of residuals. This notation means you're minimizing over all functions f of the sum of squares of residuals. It's the sum of the residuals squared. Now, note that I didn't specify here that f has to be linear. So therefore, you know, instead of specifying this linear regression, we can just go forward the rest of this talk. Just think of it as regression, because it doesn't have to be linear. And we'll get into more details about that later on. And so we will transform this into like a common loss function. You know, if I'm minimizing the sum of the squares of residuals, it's the same thing as if I were minimizing the average sum of squares of residuals. So the function f that minimizes this is also going to minimize 1 over n of f, obviously, right? Because you know this is always greater than or equal to 0, and then so 1 over n is always also greater than or equal to 0 because n is non-negative. You get the idea. And so this notion of the mean of these sum of squared residuals is called the mean squared error, MSE. This is a very common loss function. We call it a loss function because the more mean squared error you have, the worse your model is. So you want to minimize your loss function. And so when I printed out the mean squared error of diabetes y against my predicted regression of diabetes x, I got 3,890.45. Now I don't think that I'd want to have a model that has that high error if I'm a doctor and I'm actually trying to predict whether someone has diabetes based off of something. That might be just me. So going forward, we're going to expect, why do our models have these horrible, horrible things, or horrible errors? So we're going to make an important assumption here that it's not necessarily realistic, but allows us to do a lot of analysis. And it's that our data set values all come from some distribution D, give or take some error. This means that the points weren't exactly random, but there is, in spirit, some realistic correlation between our inputs and outputs. We just don't know it. It's just, there's a distribution where it comes from, approximately. So now to learn more about our errors and our predictions. So recall again that f star is our regression function. And first of all, we'll show that it is the optimal MSE solution. This is where things get a little technical, so I'm okay if people have to ask questions. So remember, f star is the minimum of the expected square error over all possible functions f. That was what we established by the min f thing, remember? And so this is also the notion of conditional expectation. And expectation, for those who haven't taken any stats courses yet, is essentially like, what do you expect a function to be? And so typically, it's usually the sum of entries times the probability of that entry if you're looking for the expectation of a function. This is a little technical, so I will understand you if you don't get this. So with conditional expectation, with the MSE loss function, what we're trying to seek is the expectation of our difference between our true target values and our model's predictions for general capital Y and capital X, so therefore for any points, but given that capital X, our data set point, is some fixed X value. Now, aren't these essentially the same thing, where if I'm given a distribution that tries to minimize the sum of squares of residuals, it's essentially the same thing as trying to minimize this expectation, or it tries to minimize the expectation. That's where we get the idea that this regression model is essentially the expected value of y given x is equal to x. Because if we have a function that tries to get the ideal y value, then that ideal y value should minimize our loss, because it's as close to the true y value as possible. So that allows us to do some math. I'll take it slow here, it's okay. So thus, for some arbitrary function f that we can predict from a model, their MSE, which is the mean squared error that we talked about earlier, was the average of the sum of squares of residuals. And I'm going to subtract and add the f star at xi. I apologize, there should be xi here. I'll fix that before I'm gone for too long. I'm going to subtract and add it. So I'm subtracting f of xi and adding f of xi. And so essentially, I have 1 over n times this ugly expression. But you'll see why I do this too. So this is kind of, if we treat it like A, like this first part as A and this second part as B, you kind of get A plus B quantity squared, which, you know, our high school teachers told us is not A squared plus B squared. It's A squared plus 2AB plus B squared. Or, you know, my teacher wouldn't be happy about this, but I'm going to write A squared plus B squared plus 2AB. But since I'm summing over all I equals 1 to n, I'm going to write the individual sums for all the A terms first, and then all the B terms, and then the 2AB terms. So why did I do this? You know, this looks like it's hopeless. This looks like it's hopeless. This looks even more hopeless. But, you know, not all hope is lost. And in fact, we're going to show that this third term right here is 0. And I'm going to try to take it, I'm going to try to explain myself as detailed as possible, although I will say it's a bit hand-wavy. So showing that that broad term is 0. So remember I talked about that expectation as, like, you know, it's the probability. If you're talking about the expectation of a function, it's the function's output times the probability of that input. Well, you could also think of this sum as over the data set. It's kind of like the expectation of like this product on the inside, where we're doing this expectation over all values in our data set. So essentially, if you take a look, let me just try to break it down as nicely as possible. If we're doing an expectation of this, then what I want to do is I want to use all data points and then divide by their probability. But the probability I select any single data point is just 1 over n, right? Because all points are going to be equally as likely to be chosen. So therefore, this is just the expectation of f of x minus f star of x times f star of x minus 1. Yeah, it doesn't get much nicer from here. However, recalling that this f star of x is equal to this conditional probability, we can write this expectation as, okay, what I'm essentially doing here is I'm taking this expectation and I'm writing it as 2 expectations, where I'm doing this expectation over the inputs to the data set, and given the inputs, what am I doing? What are my expectations for the outputs? So I'm sort of breaking down the total expectation to these 2 expectations. There's a lot of theory behind it, but I just try to give the simplest explanation possible. Now notice, this inner expectation, this e of y given x, what terms are actually having y in it? Well, this term doesn't, this term doesn't, this term doesn't, only this term does. So it's just e of y, so I can bring this e of y given x to this y. But recall that f star of x has this notion of actually being the expectation of y given x being some value. So therefore, I can replace this with f star of x. And I want to emphasize, this is kind of hard math. It requires a lot of theory. So it's a lot of take my word for it, but I'm not the best at explaining things, but I'm trying to do my best. But essentially, because this f star of x is doing its very best to try to get as close to y as possible, therefore the y that corresponds to this capital Y here is the same as this f star of x tries to reach. So therefore this it corresponds to the expectation of x with everything being the same except this y turns into this f star of x term. Now notice I have an f star of x here and an f star of x here. That's a 0 term. So therefore I'm doing expectations from a bunch of zeros, which is 0. Nice. So thus we get the MSE, if I go back to the previous slide, therefore this term gets eliminated, and it's only this first two terms. And I will go back there and describe that. So therefore I have that, there's this notion of our function and the difference between its the regression function's output and then the sum of squares of residuals of that, and then also plus the MSE, the sum of squares of residuals of the difference between the regression function and the y-axis. Now, hypothetically, what would happen if I had f, if I found f to be the exact f prime, if I found the function I found was exactly the regression function? Then this term would disappear, right? Because then f star would be equal to f. Then I'd be left with this term. These are both non-negative terms, therefore, having f being f star actually minimizes our mean squared error. And so in a notion, this proves that regression actually is the optimal solution to a mean squared error sort of problem. And so the second term here indicates the loss from our most ideal function. So remember how we said that, you can have two inputs that are really close together or the same and have different outputs? You're going to have some discrepancy there then, right? So therefore, this second term sort of indicates the difference between the most ideal function and the outputs, and the difference between the outputs themselves. So sometimes, no matter what model you have, if there's any loss here, your model's never going to be 100% accurate, and you wouldn't want it to be either, because would you want some function predicting two values for one input? No. You want to know if a patient has diabetes or not maybe. So therefore, the regression function is optimal. But why stop there, We have all this math, we have all the statistics. And sure, it can be confusing as heck. But let's go even deeper. So what we learned so far, the ideal function is always the regression function in terms of MSE. And some sources of error, which we described before, are that points are too close in the x-axis, but are far apart in the y one, or even having the same x value. And that loss is uncontrollable. So therefore, there's always going to be some notion of loss, assuming your regression function is not the same as the outputs themselves. So what can we do? We can simply just get as close to the regression function as possible. Sunglasses emoji. Well, it doesn't work like Discord. I can't do cool in sunglasses. No one laughed except for one guy. Thanks, Gordon. That's right. But it's not over. We are so back. So in that original formula, remember that second term, we just essentially realized that we can't do any better. But the first term, we can try to do better. Or we can at least expect it. So now we're going to introduce a new function, f bar. And remember how I said something about how I assumed had this important assumption that the inputs followed some distribution d, give or take some error? That's important now, because using that notion, we can actually attempt to investigate why our model could be misleading or inaccurate. So I'm going to let f bar be the expectation of our learned f of x if we choose a whole bunch of different data sets from the same distribution. So remember, there's an underlying distribution between the data points that I gave to this model. If I sample that distribution and repeat the process several times, a lot of times, then f bar would be that average function. It'd be its absolute closest to representing the distribution itself, the underlying distribution of the sample data. So therefore, remember how that distribution was D? We could say that f bar of x is the expectation over the distribution of f of x, the model that we end up getting out of a data set. And going forward, we could expand this first term right here. And so what I'm going to do is I'm going to do the exact same trick as I did last time, except I'm going to subtract and add f bar of xi. And I'm going to do that same thing. Remember, a plus b quantity squared is not a squared plus b squared. It's a squared plus 2ab, sorry, a squared plus 2ab plus b squared. And I only write it this way because I'm going to show you once again that this is 0. How am I going to do that? More expectation magic. I swear this is the last hard mathy proof before we just go into some more conceptual things. So notice that that's that last term. If I just drop the 2 coefficient, or 2, like, that scale factor of 2, it can be written as the expectation of this inner product of just the x's. Remember, if I'm doing an expectation over the data set, then everything is equally likely to be chosen, so its probability would be 1 over n. And therefore, over the entire data set, it would be the expectation of that product. And however, if we recall that f bar of x was this expectation over this underlying distribution of sample points, we have that this expectation is equivalent to. So this time we're doing the expectation over the whole distribution, the whole underlying distribution, and the whole input space. So I'm going to write it with a lot of theory. You can write it as e of x, the expectation with respect to the inputs, of the expectation with respect to the distribution. A lot of theory that I wish I could explain a little better, but I couldn't, of this thing that we got from over here. Sorry, here. And remember, keep in mind, this f bar was already written in terms of this distribution. This f bar is also written in terms of distribution. This f star isn't going to change from the distribution itself because this was only dependent on the outputs. So therefore, the only thing that actually has this e of d in it is this f of x term from here. But remember, e of d of f of x is just f bar of x. So I can just replace it with f bar of x, and this first term has f bar of x, and f bar of x subtracted 0. The expectation of a bunch of zeros is 0. Nice. So what did we just do? I told you that that third term is 0, right? This third term is 0. So I'm left with this first 2 terms for this first term, and then this second term was that term that we couldn't reduce any further. So that leaves us with 3 terms. And I'm going to rearrange this thing to put like this over here and this over here, simply because it's a nicer way of saying what I'm about to say, instead of having to like mumble jumble the order of it. So let's recap what we just did, because this is a lot of math. And remember, I don't expect you to understand the math. You can always look back to see if you want to understand the math. F is the function we learn. F bar is the expectation of the function if we sample the underlying distribution several times, and then taking the expectation across that distribution. And then f star is the regression model, which is it is a function that represents a conditional probability, and it could just be linear regression if you're doing a linear model. It's aka the function that that depicts the expectation of y given x is equal to x, doing your best training possible for all inputs x. So let's look at the 3 terms deeply. There's no math here. I'm just simply inspecting. So remember, our MSC was that. And so this first term is the difference between this f bar of the input minus f star of the input. This is the regression. This is the expectation across the distribution. This is known as the squared bias. This bias is introduced because we assume things about the model itself. Say, for example, the degree that we want the model to be. Or maybe your function or your process to get a function assumes other things, like maybe the inference is up to 0. I don't know. But essentially, the discrepancy between the the regression and the expectation across the distribution, it would be 0 if you had no assumptions and you had infinite compute power and your model just got there in the end. But there's going to be bias if you have assumptions, which realistically you will, because you don't know things about F star simply because you just don't know it. So the assumptions will give you will correlate to this bias term, or this squared bias term. The second term, which is the discrepancy between the calculated outputs from the function you learn, and then that with the difference of the function that would be from the expectation across the entire data set, the underlying distribution. That difference is actually variance. So you have a bunch of different functions that it could have been. And there is this sort of ideal, hopefully ideal function, f bar, because of the way you imagine your data set, you imagine your distribution of the points to be. Well, that difference is variance. It's like kind of like telling you, hey, you're like a little bit off from like the model that you could have been if you knew the distribution. And so it measures how far away is our model compared to the expected model if we had repeated sampling of this data set sampling distribution. So if you had sampled several times and you took f to be this average, you would be pretty close to f bar, if not get it. It represents how unlucky you are with your data set compared to the distribution that the data set is taken from, and could be influenced by the noise of the data set itself, which leads to the third term. The third term is the difference that we said we couldn't actually do anything with. It's the difference between the regression model and the outputs that you actually get, or you actually observe in the data set yourself. Now, what is that? Remember how we said that this model has, we assume this model to be of some sort of distribution, but if it was some sort of distribution, then the regression would get it. It would be able to predict it perfectly. But it's not, so therefore there's some noise in these yi's. They're slightly off from this ideal function that it should have came from our assumption. So it's things you can't control when you try to create a function. Remember, we want this data set to come from some distribution, but this suggests that there's noise between the distribution and the points themselves, and you can't really do anything about that. So how does model complexity affect these terms? When you're training a model, should you go with like when you're given like a data set, how do you know that you shouldn't just go a 100-degree polynomial in your training? Or how do you know that you should only go with a 1-degree polynomial in your training? Well, the bias, the larger the model, the less bias there is. This is because you can be potentially closer to the regression model. This regression model, remember, is this ideal function that the points are distributed from. And so the more freedom you give to the model itself, the less bias it should inherently have. Variance, however, is the opposite. You can't have everything you want, right? The larger the model, the more variance you can have, because there's more room to be wrong compared to this expectation across this sampling distribution of your data points. And finally, noise, this last term. I've said it enough times, you tell me, what is it? How does the model complexity affect it? Come on, there's one right answer out of two. Okay, I see some notes, good. Because that is represented by noise in the data itself. So yeah, what did we just do? We wrote this mean squared error of our data points in terms of 3 individual terms, which we can each explain as different phenomena. It allows machine learning engineers to be able to inspect what they're doing and how it's affecting the machine learning model in terms of being able to optimize it. Is okay, maybe the degree I'm giving it, like allowing it to go to degree 100 is too high, and therefore the variance is crazy. I gotta lower it down. It allows you to sort of like play this game of like hide and seek of, okay, not hide and seek, tag, I don't know, like cat and mouse of like, okay, am I too far, my variance is too high, or am I too little in my restrictions and my bias is too high? I say that backwards? Yes, I did. Am I too little that my variance is too high, or am I too far in my restrictions that my bias is too high? And that is known as the bias variance decomposition. It sort of explains and allows you to play this cat and mouse game as to why your model isn't performing optimally. And then this thing is just, I don't know, mouse? Like, there's no winning here. You won't be able to minimize that term any further. So models will always have the sense of inaccuracy, but the bias and variance can be toyed around with. And I recommend you try it out for yourself. Try getting more complex data sets. It's a little bit intimidating, but I will say that it's a rewarding experience to at least try to see, and there's plenty of tutorials about it to learn from. So yeah, that is my talk. Thank you for watching. Feel free to take another look at the slides, and the demos can be found there.